Okay, today is 8.1 Similar Polygons. Our essential question is, how are similar polygons related? Okay, and in order to talk about similar polygons, we also need to talk about proportions, which I know you guys have done a little bit of review on proportions, and we're going to do a little bit more right now. So, starting off with a proportion, well, a proportion is an equation stating that two ratios are equal or equivalent. And two quantities that form a proportion are proportional. So here's a proportion. And a couple ways that we can double check that they are actually equal is, for example, in this one, I could say, well, 3 times 2 would give me 6, and 4 times 2 would give me 8. So I'm basically multiplying top and bottom by the exact same number, which is really like multiplying by a 1 here, right? Okay, so that's one way of doing it. And another way of doing it, which you'll use as these become more and more complicated numbers, is to cross multiply. You're not allowed to cross multiply anytime you want. You're only allowed to cross multiply when you have two equivalent ratios or two fractions that are set equal to each other. Okay, so this is a fraction set equal to another fraction. So one way that I could actually do this to have no denominators is I can multiply both sides by 4, right? If I wanted to get rid of this 4 over here, multiply both sides by 4, and then multiply both sides by 8. Well, a shorter way of doing that is just cross multiplying. So basically I multiply 6 times 4 and I get 24. And I do the same thing going the other way and I also get 24. That tells me that these two actually do form a proportion. They are two equivalent fractions. Okay, so that's basically what you're going to do here. So I'll do a couple of these examples with you and then you can do the rest on your own. So I'll do 2 and 6 with you. So number 2, I get 6 over 8 and 15 over 20. So the question is, if they form a proportion, then they are equal. Now, a couple ways of thinking about this is like, how can I get them to be the smallest? Because to me, it doesn't make any sense. How do I go from 6 to 15? But if I can basically reduce them to the smallest possible fraction that I can get, then maybe I can see if those are equal. So one thing I can do is divide top and bottom here by some number that they have in common, basically their greatest common factor, which is 2, and I end up with 3/4. And here the greatest common factor is 5, so I'll divide top and bottom by 5, and again I'm allowed to do that because it's like dividing by 1. And here I also get 3/4. So that did work, right? So they are proportional and I can say yes. Another way that I could have done this, and now these are bigger numbers, so they get a little bit more complicated when it's bigger numbers. But because I see that I have two fractions set equal to each other, I am allowed to cross multiply. And when I cross multiply this way, 15 times 8 gives me 120. And so does 6 times 20, 120. So either way I can see, in fact, these are two equivalent fractions. And my answer for number 2 will be yes. Okay, I would encourage you to get used to the cross multiplying because you're going to end up using that a lot. And you can also think to yourself, hey, basically what I'm doing here is I'm multiplying both sides by 8. And by doing that, I'm reducing that side by 8. Here, I'm basically going to get 120. And then on the other side, I'm going to now multiply to get rid of the 20s. And on this side, I'm getting 20 as well. So that's really what cross multiplying means. Okay, you're only allowed to do it when you actually have two fractions set equal to each other. Let's also do number 6. So I've got 6 over 15 equals 9 over 36. And again, some of these are not that intuitive, so, cross multiplying for this one makes it a little bit more challenging, but still doable. You may instead want to say, let me reduce this. Let me take out the greatest common factor. So if I divide top and bottom by 3, I'll get 2/5. Top and bottom here by 9, well, I get 1/4. So right away, I know that this is a no. If you wanted to instead do it as cross multiplication, because in fact, they are two fractions set equal to each other. Then you would go 9 times 15, and that's not so obvious to me, so 135. And then 36 times 6, 216. So in fact, these are not equal, so this would be a no. And I'm going to cross off the equal signs because they don't work. All right, so that's page 1. Okay, so this is what I was talking about on the previous page. So in the proportion A over B equals C over D, the products A times D and B times C are called cross products. So to solve proportions, use the cross product property. That's going to be the best way to solve proportions. So sometimes what you're given is you're given these things that you have to solve. Solve means to get a variable by itself. And in order to do that, cross multiplying is going to be the easiest way to do this. So I'm going to do a couple of these with you. I'll do number 11. All right, so I have 21 over 2 equals 42 over D. And I have to solve for D. I have to get D all by itself. So I see that I have two fractions set equal to each other, and I'm going to cross multiply. So this gives me 84 when I go down here, and then this gives me 21D. Now I've just got an equation that I have to solve. So I'm basically going to divide both sides by 21 to get D all by itself, and I'm going to get that D equals 4. Not complicated, right? Don't worry, I'm going to make this way more challenging, just not in this lesson. Okay. 18, let's do one with some fractions. So I got 4.8 over 1.5 equals m over 4.5. Okay, nothing new here. I'm just going to go ahead. I see I have two fractions set equal to each other. I got to get m by itself. I'm going to cross multiply. And then 4.8 times 4.5, you can either do long division or you can put that on your calculator. Or long multiplication, sorry, not division. And I ended up with 21.6. I would encourage you, something with the decimals, you're totally welcome to use your calculator. Something without decimals, though, try not to use your calculator. Okay, and then I'm going to solve for m. And we get m equals 14.4. And I know right now you're like, why are we doing all this? And I promise you're going to see why we're doing this as time goes on. We've got lots of lessons where we're going to be using this. And it just continues. You'll continue to use this in future math classes. All right, so we're going to talk about similar figures. And I've asked you to look through pages 418 to 421. So go ahead and take a couple minutes. Open up to page 418 or 421. I'm going to do that on Big Ideas. All right, so talking about similar polygons, using similarity statements, so we'll start with that. So if you remember when we talked about transformations, section 4.6, two geometric figures are similar figures if and only if there's a similarity transformation that maps them. And that similarity transformation was always basically using a scale factor to either increase the size or decrease the size. So if you remember, two similar polygons were basically two polygons that had the exact same shape, so the angles were all going to be congruent, but they were different sizes. And they were different sizes basically because every side had been multiplied by the scale factor. So another key point there then is that ratios of corresponding side lengths are going to be equal, or they're going to form proportions. Okay, so we're going to start with those couple or a few things and add those to our notes. So I'm going to head back over here to my notes. All right, so let's start with the similarity statement. And I'm going to go ahead and use two triangles. I think I'll draw them over here. So I'm going to do triangle ABC. And I'll go, how about this side's 3, 4, 5. This is actually a Pythagorean triple triangle. So it ends up forming a right triangle. And then I'm going to do a bigger one. Let's pretend like these are proportional, like they're multiplied by a scale factor. And we'll make this one DEF. And so the scale factor here, I'm going to actually double it. So this was 4 multiplied by the scale factor, we get 8. This was 3 multiplied by the scale factor of 2, we're going to end up with 6. This was 5, so this will be 10. And again, this is a right triangle as well. So to say that these two triangles are similar, we can say then that triangle ABC is similar, so it's just this tilde sign, to triangle DEF. Okay, and if you remember then, let's just recall the scale factor. So when we learned about scale factors and dilations, we said we usually use the variable k to represent scale factor, and it was the image over the pre-image. So if I said, okay, I went from this small triangle to this bigger triangle, and that was the transformation, then I would just pick a side. So for example, how about we use 6 here? That's my image, right? The new polygon over my pre-image, which was the original. And as I had said, I had doubled it. So your scale factor here is 2. And if we had gone the other way, if this was our pre-image and that was our image, then our scale factor would be 1/2. All right, corresponding angles in similar polygons are going to be congruent. That's what keeps the two polygons the same shape. They're just different sizes, again, because we have the scale factor that's being multiplied to every single side. So I can say that angle C is congruent to angle F. Those are actually our right angles. I can also say angle A is congruent to angle D, and angle B is congruent to angle E. Okay, so this is just writing out which angles are congruent, so congruent angle statements. There is a dilation by a scale factor. If it gets bigger, that scale factor is greater than 1. If it gets smaller, that scale factor is going to be somewhere between 0 and 1. So if we take the ratio of any two corresponding sides, like we did here, it's going to equal the scale factor. Now, the last thing that we talked about on that page is that corresponding side lengths are going to be proportional. So you can basically take any two sides, create a scale factor with them, okay, so write them as a ratio, and then set them equal to another pair of two sides. So for example here, I'm going to take DF, set it over AC, okay, because I'm going to take my image over my pre-image, and that's going to give me my scale factor. So if I take DF and put it over the length of AC, and then I can set that equal to any other ratio of corresponding sides. So maybe I'll go with EF and BC. Basically, both of these are going to give me the exact same scale factor. So I can say, well, this is the same thing as 6 over 3, because DF was 6, AC was 3. EF is 8, and BC is 4. So you can see right away, well, they both equal 2. Or another way to check this is with, because there are two ratios set equal to each other, we can cross multiply. And so I use cross products there to check. So we know that these, in fact, the corresponding side lengths are proportional. Okay. Let's see. So a couple more things here have to do with the perimeters and the ratios of the areas. Okay, so let's look at that real quick here. We'll do some of these problems. Let's see, is this it? Okay, here we go. So starting with the ratio of the perimeters, if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding side lengths. Okay, so it's basically corresponding side lengths give us our scale factor, right? So a ratio, oops, you can't see what I'm doing. A ratio of the side lengths is image over pre-image. Or like we did here, the big over the small gave us 2. So we can say then that the ratios of perimeters is going to also equal the scale factor. And let's just prove that. So let's talk about the perimeter of each of these. Perimeter just means you add up all sides. So the perimeter of triangle ABC. Well, that's 3 plus 4 plus 5, so it's 7 plus 5, that's 12. 12 units, I don't know. We didn't specify what our units were. And then let's compare that to the perimeter of our larger triangle, DEF. 6 and 8 is 14, and 10 is going to give us 24. And let's see, so if I take these two, now I should take the bigger and put it over the smaller because we're doing image over pre-image. So if I take 24 over 12, I get the scale factor. Okay, and then the last one we'll talk about is the ratios of the areas. Okay, so let's see what that one says. If two polygons are similar, then the ratio of their areas is equal to the squares of the ratios of their corresponding lengths, or the square of the scale factor, right? Because again, ratio of corresponding lengths gives you your scale factor, and you're going to square that. And I'll give you an example of that. So the ratio of the areas is equal to the square, like raised to the little 2 power, of the scale factor. So I used right triangle so that finding the areas would be really, really simple. So the area of any triangle that you've been given base and height of is basically 1/2 base times height, or base times height divided by 2. Okay, so let's find the areas of each of our triangles. So the area of triangle ABC, well, base would be 4 and height would be 3 because base and height have to be perpendicular to each other. So it's half of 3 times 4. Which basically, I'll put parentheses there, which is 12, half of that is 6. Okay, and then let's do the area of triangle DEF. Well, it's going to be 1/2, and then again, we're going to do base times height. I got 8 and 6. So it's 1/2 of 48, which is 24. Okay, so now what I do is I take these and I set them as a ratio. So I go 24 over 6. Okay, so that's the ratio of my areas, and that should equal the square of the scale factor. Well, what is my scale factor? My scale factor is 2, and I should square that. Is this a true statement? Yeah, this is 4 equals 4. So that totally checks out. Okay, so the rest of this, I believe, are examples. And you can find these examples in your big ideas. So, for example 1, you're going to go back to the first example 1, which is right here. Now, I'm zoomed in, so I can't click on the actual play button. But if I zoom all the way out, it becomes a link that I can click on. And you'll notice that it's the exact same problem. And somebody will walk you right through this.
Triangle ABC is similar to triangle JKL. Part A. Find.
So I'm going to let you do that. So you have example 1, 2, 3, 4, 5, 6. And then we're going to do a little bit more of this practice together. You'll notice I've given you a lot of practice with proportions, and that's for good reason. So how about, which one should we do? Why don't we do number 8 together? And then I'll be done with this video and let you go watch the rest of the examples. So the only difference between this one is that when we are cross multiplying, notice that one of the either numerators or denominators, in number 8 it's the numerator of the second ratio, has 2 terms. So you're going to need to do some distributing here. Okay, so I'm going to go ahead and I'm going to cross multiply because it is a ratio, two ratios set equal to each other, so it is a proportion. Now when I cross multiply, I'm going to be really careful because I have these 2 terms here. So when I go 6 times this quantity, I'm actually going to write it out. 6 times 7n plus 9. And then when I go down to the right, that's just 45. But you can see it's not just 6 times 7 and then add 9. It's 6 times that whole quantity. So you have to actually distribute. So you get 42n plus 54 equals 45. And if I subtract 54 from both sides, I get 42n equals negative 9. And then heading over here, we'll divide both sides by 42. So I'll get n equals negative 9 over 42. And I think they can both be divided by 3. So this would be negative 3 over, is that 14? Let's just double check that. 14 times 3, will that give me 42? Yeah. So there's my solution. That's what n equals. Make sure you show all your work, please.